Hi, I'm Fabio and welcome to the eighth course about the Python Introductory course series by martechpost.com. In this course we will briefly discuss how we can manipulate images and perform some computer vision tricks using Python. As you can see here, I've already prepared the project folder. In particular, I have already set up the virtual environment, which is a standard Python environment, virtual environment, with only a few extra libraries that we will see when manipulating the Jupyter notebook. Also, in the data folder, you can see the three images that we will use in order to perform and manipulate the images using Python. We will use the Lina image, the peppers, and the tulips. Also, as you can see from my terminal, I've already activated the virtual environment and launched the Jupyter Lab. So let me show you what we see in this notebook. Okay. In this notebook, is divided in two sections. The first one discusses about basic functions in order to manipulate images. The second part will instead discuss about some computer vision tasks we can do in Python. These are just examples. We will not cover everything we can do with images, of course. Also, the three images I just showed you are a part of the standard test image library. Clicking here, we can retrieve the Wikipedia page, which tells us that a standard test image is a digital image file used across different institutions to test image processing and image compression algorithms. So the standard test image is an image which is often used to compare different image manipulation libraries, tasks, and so on. In the first cell, you can see that we import the pill library, and in particular the image class, the image object from the pill library, which is called, this is an abbreviation for pillow, which is a standard Python library that helps us to manipulate image. And also we import path from pathlib. With the path, we retrieve the fact that the directory in which we store the data is in fact data, and this is stored as a global variable called images. How computers see the image? Well, a colored image is interpreted as a sort of 3D matrix, also called tensor, because here we have a matrix, but since a colored image is represented in three colors, the RGB colors, red, green, and blue colors, also called channels. This is an image is a stack of three channels of matrices. Each pixel then can be identified by a row, a column, and three channels. the combination of the three channels gives the color we perceive for that pixel. So let's first import an image, and in order to do so we will use the pillow library, and in particular the image class. So we will call the image will be the imported image, and the image can be retrieved using image.open, and then we pass as argument the path to that image. Here we are using pathlib, so we have to return a string of a pathlib object, which is images / we will use the tulips for now, the tulips image tulips.png. Excuse me, I didn't whoopsie, I didn't run this cells, and now okay. Images, this image object has several properties we can see. For example, we can retrieve the format, which is PNG. We can retrieve the size by typing image.size. And here we can see that it tells us just the dimension of the matrix without telling us the fact that we have three channels here. And then we can, for example, study the mode of the image, which actually tells us is if the image is in RGB or, for example, in grayscale, and so on. So here we can see that the image is stored as RGB. With these two information, we know that we are dealing with an image in this format, with row, columns, and channels. Okay. Another parameter of image is the info parameter, which is a dictionary, and in order to retrieve the keys of this dictionary, we can do something like this. We have the gamma, the chromatosity, and the DPI, for example. For example, here, if we want to, we can retrieve the DPI of the image by typing info and retrieving DPI 72,72. Okay. We think to have imported the image correctly, but we are still unable to see it. So let me show you how to display that image. We have just to type image.show. With this command, another window will open, and let me show you what you can see. Just let me capture the window. You can see something like this. You can see here that the standard, it's open with the standard program in Windows that opens images. Okay, let's close this. Just let me set up a little bit. Okay, let's close the open image and continue. We can do something else. For example, maybe we would like to rotate this image. In order to do so, we just type image.rotate. So we call the rotate method of the image instance, and we type the degree. For example, we want to rotate the tulips by 45 degrees, and then we can type show. another window will open, and we can see something like this. You can see here that the image is rotated by 45 degrees and the space left is colored in black. Nice. Let's continue. We can do also other things. And the funny thing is that this command returns the image. With this in mind, we can use the with statement in Python. So with the image, let me copy directly so we don't make this mistake. So with the image that is opened, etc., as image, we can use the image inside the with statement. For example, we could maybe crop the image. In order to do so, we have to define the box that splits the image. So for example, we want a box with the left position will be 200, the upper will be 100, the right will be 500, and the lower will be 300. We will see in a minute what these numbers mean. Then we type region equal image.crop. Crop using this box. We can also type region.show. And here, let me update. Here we have the cropped image, as you can see here. Okay, we can also perform other operations. For example, there's a general method called transposed. We call this method by typing, of course, transpose, and we pass an argument. This argument could be image.rotate 90 degrees, and we would get the same result as if here we put 90, the number 90. The transpose with rotation is less flexible because we are passing an image variable, and of course the library does not encode all the possible angles. But we can also perform other transformation. For example, we can flip left to right by typing flip left, right. Let's type show then in order to get the result. Okay. Let me show you. Okay. And here you can see that the flower is transposed with respect to a vertical axis. With the pillow we can perform several transformations, but generally speaking, pillow is a basic library and also sometimes can be slow. slower than OpenCV, the OpenCV library, which is also called CV2. As you can see here, as Python, CV2 is the Python, the name of the Python library, and the standard requires that this is imported as CV in general. Here we have NumPy, because NumPy is, as we have previously seen in the previous courses, is an extremely efficient library that enables to deal with the matrices, and an image is a sort of matrix. Then we have the matplotlib pyplot library, because we will see that with OpenCV, the OpenCV library, and with the pyplot library, we can still print images. We will perform in the next cells, we will perform transformation using OpenCV. So why not use OpenCV to import the images? In fact, we can do this. For example, tulips can be imported using the cv.imread and typing the path to that image. tulips.png. Excuse me, I always forget about importing this. Okay. The thing is that we can also display the image by typing, for example, cv image show, and then the title of the image, for example, tulips, and the stored image, tulips. Then, in order to complete the execution of this cell, we need to type cv.waitKey 0 and cv.destroy all windows. Now we can run this cell. As you can see, the cell is still running because I didn't close. Let me grab the image. Here we go. Because I still didn't close this this picture that you can see here. This picture then can be now I will close this pop-up, and automatically you see that the cell completed its execution. But let me rerun the cell. Now everything is good. Okay. The thing is that OpenCV expects the BGR channel, not the standard RGB channel. That's why we have seen that the tulips, I rerun the cell. You can see that the tulips are displayed correctly. There's green, red in the right places, so that's fine. You may think that the image is imported correctly, as per the standards. but that's not true. And this is because OpenCV expects BGR channels when showing an image, but also reads the image, storing each channels in the blue, green, red order, while all the other libraries use the RGB, the standard. In fact, let's try to display the imported image here, the tulips, using another library. The simplest one is pyplot. So we just need to type plt.im show, and we type the tulips, and then plt.show. You can see here something is wrong. What's wrong? Well, for example, here the tulips should be red. Instead, they are blue. Why? Because pyplot expects RGB, but finds the blue colors instead of the red ones. That's why the tulips are blue here and not red. One way to fix this is to switch the channels. For example, by typing tulips is equal to cv.cvt color, and we pass as arguments the original image tulips and then the way we want to switch the channels. For example, here we want color BGR to RGB. We rerun, and finally the image is displayed correctly. I want to mark two things here. The advantage of using pyplot to display image instead of using OpenCV directly is the fact that when dealing with Jupyter notebooks, we can store the image inside the Jupyter notebook itself. Instead, with OpenCV, or we have seen previously with the Pillow library, the images are displayed or opened using Python, creating a new pop-up, a new window, or opened with this library, the software binded to open that type of images. For example, for me was the standard library software used in Windows. Instead, with the pyplot, the image is displayed correctly in the Jupyter notebook. Also, I want to point out another thing. Here you can see that the y-axis is inverted. 0 star, the origin of this axis, begins on the top left corner. That's why here in this box 200, which is the left corner of this box, and for example, let's take the left upper corner. We have typed 200, 100, which means 200 here, 100 here. The top left corner, which is correct. And what is the bottom right corner? It is 500, 300. 500, 300 here. So the box should be something like this. Okay. Previously we have seen that we have 3 channels, and these channels can be stored as an array of 3 elements. One for the R channel, one for the green channel, and finally one for the blue channel. In this way, using the RGB standard, remember, we can bind some colors, some basic colors. For example, black. We can display a pixel with a black color when the RGB tuple is refers to 0, 0, 0. A type of gray can be displayed using 128 for both channels. White is 255, and 255 is the maximum value a channel for that pixel can take place. So the values for a pixel and one of its channel has a range of 256 values from 0 to 255, where 0 is the black and 255 is the white. How you can see here that we are dealing with the RGB channel? Well, for example, here red is binded as 255 in the first channel and 0 in all other channels, and so on. Here, for example, let's run this cell, okay? Let's create a black image of size 512, 512, which are these row and columns, and with 3 channels. We also specify the format of each value, which will be an integer. We create a black image and we display this image. As you can see here, we are dealing with 512 per 512, but of course we can't see the channels. All right. Again, we can retrieve. This is basically a NumPy array, and a NumPy array. From a NumPy array, we can retrieve the shape in the same way as we have done in Pillow, just by typing image.shape. Is one of the attributes. As also specified in the OpenCV library, there's a warning. In fact, NumPy is an optimized library for fast array calculation. So simply assessing each and every pixel value and modify it will be very slow, and it is discouraged. What we mean by simply assessing each and or every pixel value. For example, we can retrieve we can create these 2 boxes, these 2 squares in the picture, just by identifying the corners of this square, which could be, for example, from 100 to 150, and these are the rows, so from 100 to 150 here, and the y's from 100 to 150. Okay, and we tell that these values must be equal to white. This here we are retrieving 50 values from X, 50 values from Y, all the 3 values of the channels, and we are passing for each of the combination of this an array of 3 values, which are the values for the 3 channels. Let's make the blue square by typing something similar, equal to 150, 250, and 150, 250, square of course, and we want the blue color. We run this, and we define a standard function that we will use in the next cells to display the image. So we have def, the name of the function will be plot image. We will pass the image, which will be an array, and we will define a figure with fig size equal to 8, just to make the pictures a little bit bigger than this one. Then we can type plot image show, and we will plot the image, and then we can type plot show me the image. Now we can just in the next can type plot image, and we type image, and here we go. We have finally. We can also access the red value. We can do it, for example, by typing image, give me the item that is positioned. Remember that image here is retrieved, yes, is defined here as a black from numpy zeros, which creates an array with all zeros as values. So image item 200, 200, 0. For example, we access the pixel in position 200, 200, and the channel, so here this pixel, and the channel 0, which is the red one. And of course is 0, because if we want to access the blue channel, for example, we type 1. The green. And if we want the blue, we type 2. And of course this is pure blue, so the only value that is different from 0 refers to the third channel. Okay, let's keep it red. Okay. We can also modify the red value here, and for example, just by typing ItemSet, we type the position of the pixel as the first argument and then the value we want. So we type 255, and if we remember correctly, here we go. If we mix blue and red together, we get a magenta. That's why here we can, for example, rerun this. Now it's 255, and we can plot the image. Maybe let's zoom if we can. Things are getting just a little messy. Maybe you are able to see the fact that here there's a pixel that here there's a pixel that is not blue anymore. That's fine. Let's move on. Another thing that we can do is the fact the most interesting thing is the fact that here with ItemSet we are not setting directly the value, but we are using a function that is optimized to do this kind of things. Now we can crop, we can select, we can create the sections extract sections from the image. For example, we can extract this section of the image by typing 115, for example, here. So we will crop 115. Just this part by typing 200. 200. Let's see what this section is by typing plot image and type sect. This section, right? Now I want to keep this section and paste it to another part of the image, for example here, in order to get this result. How can I do it? Well, I just have to refer to the same number of pixels, but in another position. For example, to 290, 365, 300, 365. All these pixels will be equal to the ones that are referred in this section array. You can see here that we are referring to 85 columns, and here to 75 rows, the same number here. Okay, let's rerun, and let's run this one. We get correctly the result. Now we would like to draw a diagonal line with thickness of actually we would like to be red, the diagonal red line with thickness of 5 pixels. Now we can we have to redefine the image, which will be the result of the line function from the OpenCV library. We pass the image and the two beginning pixel of that line and the ending pixel would be 50, 300, the starting point, and 345 will be the end of the line. Then we pass the color, which we already defined as red, and finally the thickness of the line in pixels, 5. Let's plot, and we have our red line. Now, as you can see here, we want to perform other operations. Add a circle and add a rectangle here, a bordered rectangle. We just need to call other OpenCV functions like cv2 rectangle. Pass the image and the vertex 280, 280, 440, 440. Then we want this to be green, and 5 is the thickness. And running this, we have our border. Then we can do image equal to cv circle image, the center of the circle, which will be 430, 80, the radius in pixel of the circle, 63, the color, yellow, and -2, which means that we want this to be filled by this color. Okay, we can now write a generic polygon with, for example, here we have still for vertex, by using image equal to cv.polygon, polylines, image, an array of points, which we will define in a minute, true, the color, magenta for example, and the thickness of 2. Here for example you can see that is closed. The third element, the true element, means that the polygon must be closed. So instead of passing 2 times the vertex, one of the vertex, which will be the starting vertex and also the closing vertex, by passing through, automatically the civil library draws the last line which connects and closes the polygon. Okay, the points are these ones. I just copy paste because that's not the point of this course. Okay, and we run and we get this. Fine. Now, for example, maybe we want to create a border around this picture. There's another function from OpenCV which is we want to create a border that enlarges the image. Of course, we don't want to crop the image because using a border. So we use the CV copy make border. We type the image and then the dimension of the border for top, left, bottom and right. We want the border to be the same, so 38, 38, 38 and 38. And finally we type the fact that the border should be CV border constant, and also the value must be gray. With this argument we are telling OpenCV to create a border with a constant color that must have this value, the gray value. Okay. Another thing that we can do is to another type of manipulation that we can do with images is the image blending. So we take 2 pictures and we blend them together. For example, we have the tulips that we already imported, is here. Tulips is here. Okay, is imported as an RGB picture and as this shape. In order to blend 2 images in the way we will see in a minute, we need to create another image with the same dimensions. So first of all, let's create a blank image, a blank and a black image. We will call this as circle. So np zeros tulips shape. We pass this shape and the format, which will be int 8. Now we want to draw a circle. So circle will be cv.circle. We pass the original image, and then the center of the circle, 365 to 105, the radius 100, the color yellow, and the fact that we want the circle to be filled. we get this output. Now we want to blend the two images, but to weight the blending. For example, we want the original image to be the 70% of the colors, and the left 30% of the colors from this picture here. We can redefine the image then by typing CV add weighted. We pass tulips, the first image, and the weight, the 70%, the other circle, which will be 30%. Add weighted. Of course, gamma should be equal to 0. Okay. Can plot, and here we get the fact that we have blended, giving only 30% to the fact that it's yellow. In fact, here you can see that the image around the circle is a little bit opaque because it's blended with a black color. Maybe we can do something like this, for example, circle, and in this way we get a white image because we add from all these are all zeros. We add to each of the values here 255, so we get a white picture, and then we paste a circle. Here we have a white, and you can see that adding a weight, the image in general would be brighter. We can perform other operations, but first, like the image thresholding. Let's first import another image, which will be the peppers images. So CV image read string images peppers .png. And since in order to import the image, we have used the OpenCV, we have to exchange the channels by using this function. Okay. Maybe let's plot the image. Peppers. Here we are. So let's talk about simple thresholding. Let's open up this link. There are several ways in which we can apply a threshold. For example, this is the original image. We can select a threshold for this grayscale color, and using a binary threshold, some pixel will be 0, some pixel will be 255. That's it. Then we can use the binary inverse, the trunk, in which we are truncating here. You can see we are basically truncating the color and applying this constant color to the remaining part of the picture. Here we have a 2-0 and 2-0 inverse. The options for applying this type of thresholds are defined as these parameters. So the first thing to do is to transform this RGB color in image in grayscale. So let's call this image peppers to gray. which will be just the result of the CVT color peppers, and then cv dot color RGB to gray. For example, here, what's the result? Peppers to gray. Am I missing something? Oh, of course, because here there's a problem, because when defining here we are not telling in the image show function to use the grayscale, the fact that the image is as grayscale. So let's rerun this, okay, in order to get the original image. As you can see here, you have to specify the CMAP as gray, and everything works fine. Now we have to create the mask, a sort of mask, which will be the result of the application of the threshold. In particular, we will use cv.threshold. We input the peppers to gray image. We specify the value, the threshold value. Threshold value 150. The max value, that will be 255. Oh, something 255. And finally the type of thresholding, which will be trash underscore binary. This function returns two things, but we care only about the mask. So this is the first output, we don't care about it, and the second output is the mask itself. Maybe we can take a look at what the mask is. As you can see here, the values that are under the threshold are equal to 0, the others are equal to 55. Let's continue. Finally, we have to apply the filter. So the filtered peppers are the result of bitwise. So we apply a bitwise operation, and the operation is AND by peppers and peppers, but using this mask, the mask itself. So peppers will take the pixel values of peppers will take their values only when the mask is equal to 255, otherwise will be all black. The result, in fact, this is the original image, this is the grayscale image, this is the filtered image, the mask, excuse me, and this one is the filtered image. For example, we can also look at the histogram for taking the grayscale image. Ravel just flattens the 3D array. We use 256 bins because we know that they are the maximum values that the number of values that a pixel can take in a grayscale color, and you can see that this is the scale. We have selected a threshold of 150. So if we transform the filtered peppers in RGB to gray, so in grayscale, here we are transforming the filtered peppers in grayscale. We apply the same histogram, and what we will see, the fact that there are a lot of pixels which take the value 0, and there are other pixels that here is a little bit difficult, but take value only above 170 and 150, excuse me, 150 of course. So the filter was effective. Another type of thresholding operation could be the HSV thresholding. So far we have talked about, we have described a picture as a matrix plus 3 channels, so a tensor. The 3 channels could be RGB, BGR, but have this format, this structure. There are other ways to describe the colors, and one of these is the HSV method. Here you can have more info about it. You can find the code, for example, in Python, and several other examples, for example here, and so on. I just paste a little bit of documentation. HSV stands for hue, saturation, and value, and is a model to represent color space similar to RGB color model. This model to represent the color space is more useful when we want to select a continuous range of colors, because as you can see here you have 3 parameters that pack together easily the colors. As you can see here, in RGB, using the RGB color space, it's more difficult to segment an object in the image based on this color, because the colors are mixed together in a sort of non-uniform way. If I want blue and red together here, or with a particular saturation, etc., what can I do? So the idea here is to convert the BGR or RGB picture in here is actually RGB picture to the HSV color model. So peppers HSV will be cv.cvt color peppers cv color RGB to HSV, and this is the first step. Then we can define a range of, for example, black color, something like that, and for example, or black, or in this case we actually use red color, which will be, for example, light red will be described as numpy array of what, 30. This selection is kinda empirical, to be honest. You try several colors and in order to get the selection you want, the mask you want. Then we have the dark red. There are also softwares and online websites that allow you to choose the HSV parameters. Directly showing you the color and the respective RGB and AHV tuple. Also note that, as I pointed out here, the threshold, the HSV image, that's what we will do now with red colors, but OpenCV uses this scale, while, for example, GIMP uses this scale. So we create a mask, CV in range, so the colors that are in this range, from peppers, HSV, from light red to dark red. Then, of course, what we will do, we will perform the result, which will be the bitwise operation between the original image and the mask. So here we take CV. Now we don't need anymore to use the HSV transformed image, because we already created the mask. So we can type CVT color, CV bitwise and between peppers, and the mask is mask. What's wrong here? Because I made a typo. Okay, now let's show you. I will show you what we get here. Excuse me, there's an error here. Okay, excuse me, I made a typo and I fixed the things. Simply, this was not red but light green. So when I fix this, you can see that bitwise operation between peppers and the mask. You run this, and then you run the image, and you get the original, the mask, and then the result. Another thing that the image manipulation, almost related to computer vision, is the fact that the operation that allows us to find the contours of inside an image. One way to find the contours is, first of all, to transform an RGB image in a grayscale image, and then perform a thresholding operation. With this in mind, is a lot more easy to find the contours. In fact, there's a function called find contours, which takes 3 arguments. The first one is the source image, the second one is the contour retrieval mode, and we will see in a minute what we can choose, and the third is the contour approximation method. The output are the contours, and the hierarchy. here, excuse me, here. Okay, CV dot find contours. We have the mask. Of course, we use the mask. CV dot retrieve 3 is one of the contour retrieval modes, and then CV dot chain approximation simple. One of the problems with the CV with OpenCV is the fact that drawing contours to an image overwrites the image itself, even if it outputs the image with the contours. In order to avoid to lose the original image, what we can do is to create a copy of it by typing peppers contours are peppers dot copy, and finally peppers contours are the result of CV draw contours pepper contours, and then we pass the contours -1, and finally the color, which will be blue, for example, and then the dimension of the line, the line size of that contours. We run, and we can run also this cell which displays the original image, the grayscale image, this mask that we have applied, and then the contours that the find contours defined. For example, here we can see in a bigger picture the contours themselves. The last argument that I want to cover are the filters developed using convolutions. Here you can find, in this link, you can find more information in the OpenCV documentation. For example, here you can see a kernel, a 2D filter, and here you can find more examples about kernels that you can apply. But first of all, I want to introduce you how convolution work, and especially what they are. The main element of the convolution operation is the kernel, which is a matrix that is applied to the original image here with the convolution operation. Basically, what you do, you take the kernel, you project in a sort of way, starting from the top left corner, the kernel, and you do this operation. You multiply this value of the image times this value of the kernel, this value of the image times this value of the kernel, and you do this for all, in this case, the 9 cells in the kernel. You get 9 values, and then you sum these values all together. And here you get you get one value which is equal to 2. Then you shift the kernel by 1, getting this square, and you repeat the operation and you get again 2. Then you move down by 1 pixel the kernel and you repeat the operation. So you start in the third computation. We refer to the pixels, the image pixels 5, 6, 7, 9, 10, 11, 13, 14 and 15, and then you move. We are dealing with this operation. You can see that we are applying, there's a multiplication pixel wise, and then a sum of the results. Here you can see clearer, and then because these are the values of the kernel, 1, 0, 1, 0, 1, 0, 1, 0, 1. The output is also called the convolved feature. In order to use the another thing that I want to point out is the fact that the convolutions, for example, here you can see another application. Convolution are the basics on what are named as convolutional neural network. These simple operations can be stuck together in order to create complex mathematical models that allow, for example, to make predictions using pictures. For example, we can predict if in that picture there's a person or not, or we identify the edges of the face and some other applications. For this task, we will use the Lina image, which we can import right here. The first kernel that I want to show you is the Gaussian filter, which applies a smoothing effect to the image. So it blurs the image in a Gaussian way using a kernel that has values based on a Gaussian curve. So we refer to Gaussian blur, we type the image, the kernel size, for example 15 by 15, and then 0. Excuse me, I didn't run. Okay. Okay, that's my mistake here. Here we have the original image and the Gaussian filter, which is a blurred image. Imagine all the concepts that we have talked so far stacked together. For example, we can identify the edges, we can draw contours, then we can crop the image, for example, only retrieving the background, then apply a blurring effect using a Gaussian filter, and then stacking the original image and the blurred image together. This is a Gaussian filtered kernel. But there are also derivative-based kernel. You can find here some these types of kernel here. Here is thus the identity, of course, because you get only the center picture. Here you can have the edge detection, the sharpen, the box blur, the Gaussian blur. Here you have, for example, a Gaussian blur 3x3. That's the effect. You can see that's always a normalization term, because you want the value of the sum of these values should be equal to at maximum 1, and so on. You have the unsharp, the Gaussian blur 5x5. Well, what I want to cover now are the edge detection, because they are derivative based. Why? Let's think about this sharpen filter, this kernel. What we are doing here, we are taking this point, projected point here, for example, for the first application of the kernel would be 76, will be a positive value times 8. And then, when computing the result of the convolutional operation, we are subtracting to this value the other values around that central pixel, but stacked all together, right? Because we have -1 as all values around the central pixel. So we are computing the difference between the point in the center and the point around it. We are computing a sort of derivative. And that's where you can see the edges, where fast change between one pixel and the nearest one. The fast change is described by a huge variation between one pixel and the nearest. Here the Laplace kernel can be, for example, described as kernel is equal to -1 times, we want to write this one, and manually we can type np ones. For example, we want a kernel 3x3, like the one in the picture. And for example, np, let's take it float, is the same, doesn't matter. Then we take the central element and we force the value to 8, and then we can compute the convolution with this custom kernel. The result would be called convolutional linear. We apply a 2D kernel, so OpenCV filter 2D Lena -1 and the kernel. Here you can see the result. As expected, we see the edges. Of course, this filter is applied for the R channel, for the green channel, and for the blue channel independently, because the output will be still an RGB image. Another way to write this Laplace kernel is just to simply call the specific function in CV, which is Laplacian Lena CV This is just the format of the picture. Excuse me. This should be. But as you can see, this is more sensible. The Laplacian is more sensible than this type of kernel. In fact, usually I prefer to use this custom kernel, the sharpen filter, it's also called. Okay, the other two types two kernels that we can use to detect edges are the Sobel kernels, which are defined in this way: GX and GY. As you can see here, one GX detects this actually the vertical variation, while the GY detects the horizontal variation between pixel values. We can apply the two filters just by typing Sobel x is equal to cv.sobel Lena, the same cv.cb 64 f 10, which means that we are referring to the GX here, and then we define the Sobel Y, which takes values 0, 1. We run the filters and we get these results. As you can see here, Sobel X detects very clearly these edges, for example, vertical edges, which are completely ignored by the Sobel Y filters. In fact, for example, let me see, this one are almost horizontal lines. In fact, the Sobel X filter detects that lines, but not like the Sobel 1 filter. So that's all. That's all I want to cover in this course. I hope you enjoyed the course, the 8 modules that we have covered, and happy study and have a nice day. Bye.